we fired individually, if it is fired simultaneously, then fired with short delays, you can see the fragmentation that is taking place. Now, based on the field visit that we have done, we came up with some corrective measures which can be used in the press plate design and blasting. So we suggested that press plate design auditing should be done. Then the angle adjustment informations. Then we should also have a press plate drilling team, which can also be used to improve operations. And the use of inclinometers, which can also be used. Then the hole spacing, currently they were using this thing, let's say a hole spacing, which was 2.5. Yes, that was what is used, so 2.5. So we can also optimize this hole spacing. Then we also have highly jointed rocks. If you have highly jointed rocks, the spacing, you should also look at the spacing, which is that. Then we can also use some of these drill rigs, such as the DTH, in order to minimize these deviations. Now, how do we assess this press plate, the assessment? We have a common tool which is known as the half-cast factor, which is used to assess the press plate barrels, which are shown on the pit walls. So you can see in the diagram we have here, these are the barrels which are shown on the wall. You can see this an improved press plate. You can see the spacing between them. So we are able to calculate this half barrel. So I calculated one. See that we are having 91.67, which is showing a good or improved press plate for the site. Now, at this point, I'll hand over to one of my co-PI to continue with the slope failures analysis.
Good day to you all, distinguished panel and fellow participants. I am in the person of Alvin Kwatin Kobi, and will be presenting on the topic, slope stability analysis. So in Ghana, the most commonly preferred method of gold extraction is the open pit method. This is due to the notable advantages that open pit mines have over the underground mines. Some of the advantages include reduced cost and also faster production rates. But with its advantages comes some disadvantages, which example being slope instabilities. So the cost of remediation of failed slopes can be quite high, and it is therefore of high importance to actually carry out analysis in order to prevent these failures from occurring. So Flag 3D software was basically used for the analysis, and Flag 3D is also an explicit finite difference program that is used to study the mechanical behavior of a continuous three-dimensional medium as it reaches equilibrium or steady plastic flow. So in order to perform the analysis, a 3D model was created. A DXF file was first of all created in SEPAC, and then it was imported into Flag 3D building block pane. So the DXF file together with the building block pane was used to actually create a 3D representation of the pit under consideration. So this is the DXF file that was created in SEPAC, as shown in figure 1. And also, as seen in figure 2, the control point of the building block pane of the Flag 3D was used to map the surface of the building block model to match with the DXF file that was imported to create a realistic or more accurate impression of the pit under consideration. Okay, so after the model was created, it was time for us to actually assign or attribute geologies or characterize the pit with geologies. And the major geologies which were considered are the metavolcanics, the metasediment, and the graphitic mylonite. And due to, or because of the geological set of the mine, the Mole-Coulomb constitutive model was used for the analysis. So this is basically a stratigraphic section of the geological unit as sourced from CABA 2013. Okay, so after the geology was characterized, this is the results as seen in figure 5. So in order to actually calculate or verify where there will be likely failures in the pit, the strength reduction technique was utilized. And with the strength reduction technique, it basically reduces some properties of the zones, properties we specified for the model. It reduces the properties like cohesion and also the frictional strength of the frictional angle of the 3D model. So for Flag 3D, it basically uses commands, just like scripting of codes in Python and other languages. Flag 3D basically operates using commands. So a data file of command was created in order to solve the model, in the first case, to a convergent state or a state of equilibrium. And another data file of codes was also created to actually solve the factor of safety of the pit under consideration. So below is a summary of basically the methods that were used in order to carry out the analysis. So a 3D model of the pit was created and it was calibrated to a reasonable extent. And also zone properties and materials were assigned to the model. And because groundwater has an effect on the stability of the slope, groundwater conditions were also imported into the model. And also boundary conditions were applied to all the northern faces, the south faces, and the other faces of the model. And after, the factor of safety was computed for. And finally, the interpretation of the results. Okay, so the data file was created to actually solve the model to a converged state. And as seen in figure 7, that is the model at its equilibrium state. And this equilibrium state was then used to actually calculate the factor of safety of the pit. So for factor of safety calculations, basically Flag 3D computes a characteristic number of steps. These are the steps in which the model would reach equilibrium or come back to a converged state. So after the characteristic number of steps was calculated for, a first stable state, a first stable FOS was calculated for. And after, a first unstable state was also calculated for. And Flag 3D basically utilized these two states in order to compute the more accurate value or more accurate FOS of the slope. Okay, so as I stated earlier, groundwater has a significant effect on the stability of slope. And they basically change the stress state of the rock, the surrounding rock of the pit, and also increased pore pressure results in a reduction in the shear strength of the rock units in the pit. So groundwater also showed a significant effect on the stability. And also fault areas they were likely to create paths for entrance of groundwater into the pits. And I'll see in the video on the left, we can see seepage of groundwater into the pit model. And as shown in figure 8, we can see the pore pressure gradient of the pits was simulated for. Okay, so this is a pit as a result of improper or groundwater seepage. We can see that the pit is flooded. This was due to an unfunctioning pump at the mine site, which caused this flooding that we see. Okay, so after the strength reduction was used to actually calculate the factor of safety, a displacement map was created. And the displacement map of the model was compared to the actual displacement that occurred at the pits under consideration. So as seen in figure 9 is the actual failure that occurred in the pits. And as seen in figure 10, we can see, as seen in figure 9, this is the failure surface. And as seen in figure 10, this is also what Flag 3D predicted. And we can see that from comparison, Flag 3D was able to predict the instability or where there will be likely failure to a reasonable extent. Okay, so after the factor of safety was computed for, it was compared to a failure criteria to identify the type of failure that was occurring at the site. So the criteria is given below. And as a stability criteria of the factor of safety was actually 1.3 or more. The factor of safety of the slope has to be greater or equal to 1.3. Okay, so this is basically a section view, a 2D section view as shown in figure 11, where the displacement was occurring. And the factor of safety that was computed for was 1.8. So comparing the factor of safety that was attained, we can see that the failure that was occurring in the pit was actually a circular failure, as shown in figure 13. Okay, so Flag 3D was basically able to predict to a reasonable extent the failure that occurred in the actual pit. And also the zone pore pressures were calculated for. And with the zone pore pressure, this will help the engineers to better design, create informed or take informed decisions to create sumps at the pits where they can use the sumps to actually dewater the groundwater that will be seeping into the pit floor. So in future works, the effect of rainwater from literature, rainwater also has an effect on the stability. But in this case, the analysis was done in a dry condition. And in future works, we are going to consider the effect of rainwater coupled with the groundwater seepage to see the stability of the pit.
Okay, so we move to the other part of our work. Usually, that's the short exploder and the continuity circuit tester, which is used. Usually, when we are at UMAT over here, we'll be here, then we hear some vibration. Yes, today you are going to see the tool that is used to give the initiation system. So usually, the old system of initiation is the plain detonator and the safety fuse that is usually used. And this, it has a high accident potential. Then if you want a better breakage and high productivity, yes, and it can also cause problem to blastmen, such that you have to linger around the face in order to what? In order to light all these safety fuels. But we have gone past that stage. But if you go to most of the areas where galamsey is still going on, some of this initiation system is still currently being used. So we have the safety fuse, which is also here. You can see how it's burning. Then we have this thing you can see in the diagram over here. This is a typical rock that we have the safety fuse that is being used. Then you can see the detonation that is taking place when it's being used. You can hear the sound. So basically, this is what is being used. Then with our short exploder, this is the first trial we made and we failed. Yes, we made this short exploder and we failed. It didn't work. When we sent it for trial, it didn't work. So this was our first setup. We have to go back to the drawing board again and come out with another design. So basically, in order to test our device to show that whether it is working, we were able to prepare a black powder where we use sulfur. Yes, sulfur, we bought sulfur at the market. You can see in the diagram here, this is our charcoal, this is the sulfur. Then we got potassium nitrate from Takwa Secondary School. They also assisted us. So we were able to prepare this powder over here, which we use to test our device. So you can see the specification of our device. We have the nominal hot firing voltage. We have the nominal output energy, which is given there. Then it has a rechargeable battery of 8 hours, which is also given there. Now you can see this is the trial with the gunpowder we prepared at the lab. We are also grateful to the mineral lab. We were able to carry out that research over there. So you can see this is the short exploder that we have been able to develop locally. So you can see that this is the first trial that we did with the exploder. So now you can see this is our continuity circuit tester. Usually in surface mine, we have the connectors. If they connect all the holes, we need to test for continuity. So this is the device that is here. This is the device you'll be able to produce, which was used in the mine for the testing, for the circuit testing. Now we have a typical underground mine. We have the ring design, which is used. We have the boreholes here with the delays at the top. So this is the ring design, which was done in data mine. So you can see our device was first used for the first underground portal blast at the mine. So we can see the fragmentation, which is here. So they are opening a new portal, and our short exploder was used in order to carry this first blast over here. Now, this is the mine site where the drilling operation is. This is the drilling cabin. We have the console, which is there. We have some causes of hole deviations, which are also enumerated over here. Yeah, so basically, we were also able to model the rig. We were also able to model the rig. You can see this is an ongoing project. We are still on it. We are able to model the rig at the drill site. So because we know that these borehole deviations, they can have effects on the mining pit wall. So we are it's currently an ongoing project. You can see this the rig that we have here. You can see the drill string going down, making a hole. You can see it in the video over here. Then we also have a situation where we simulated the whole deviation. So you can see the whole deviation. You can see this is the formation. This is the formation. So you can see we're able to model it. You can see the deviation that is taking place underground. So you can see. So we have the actual path. So this is what if you have some discontinuity in the formation, you can see some of this. You can see this is typically what actually happened underground, where you usually have those whole deviations. So you can see that in the initial images that I showed, you can see that we have these pre-splits, which are usually not following the actual hole design. So you can see the whole deviation that is taking place over here. Then we move on to the testing of our device. You can see the engineers at the site. So we have our circuit, our continuity tester. So you can see in the diagram, the engineers are testing the continuity tester that we developed at UMAT here. So you can see it's working over there. So you can see that it's working, the engineer, so you can see it's testing it. It's testing for continuity to ensure that all the surface connectors are connected. Yeah. Then let's see how the blasting is taking place. So this is our device, which we actually produce. This is a locally made product. It's not imported. So this is the locally product that was produced here in UMAT. So you can see the engineer giving the shot. So you can hear the sound. Yeah, the shot has been given. So you can see it over there. So the device is actually working over here. Okay, so this is another blast that was also taking place. This is an AEL guy. He wants to test the product from UMAT, whether it's really working. So the engineers gave it to him to try. So you can see that the engineers themselves, they are confirming that our device is faster for the blast. So you can hear it, you can hear them speaking. They are speaking the local dialect. So that's it. And you can see the mock power after the blast, which is also given over here. Now, somebody will say, maybe we copied this from somewhere. No, we did everything from the scratch. You can see the engineers at the site, they opened the one that they bought. And this has been what? Sealed or been concealed. You can't break it. It's a tough plastic, which you can't do. So we designed all our circuit, we designed everything from the scratch. So you can see it with the evidence over here. You can't open it and say we have copied or this thing. So this is currently what they use. Then we have been able to also come out with our own. Now, this is also very interesting. After we produced the short exploder, we now went on to what cost-saving effects. Now, you realize that in the mines, they use harness wire. This is the harness wire, which is being used for firing. So we came with we have the 4 power cable, which is here, which we also recommended for the mines. Because usually this one, after every blast, usually fly rods and other heavy moving equipment can destroy the firing line. So with this one, we can have a good firing line where it cannot be easily be tempered with. So you can see the engineers at the sites which are using the core power cable that we have recommended. So you can see this is also another blast. So our device has been working for the past 1 month. It's very robust. We've not had any failure yet. So for the past 1 month, the device has been working. So you can see the engineers at the site over there using it. Now, we also did some environmental assessment, especially when it comes to drilling and blasting. We have to also look at the environmental assessment. And according to the LI in Ghana, we have that what? We have ground vibration, which should be what? 2 mm per what seconds. Then we have that of the air blast, which is what? 117 decibel. So these are the regulations which are permissible in the mines over here. Now you could see this is a data that is showing the blast monitoring results that were obtained when our device was used. So you can see compared to the threshold that is given here, you can see it over here. This is the air over pressure. You can see that it falls within the requirement. Then you can see the ground vibration, which is also here, which also met the requirement for the various locations. Then we compare this to overseas blasting vibrations, which is also here, UK, United States, Japan. We also compared it to this, and you can see that what it has met the requirements. Now, another thing we also did, our aim was that we want to save costs because drilling comes with cost. That is one of our aims. So you can see that in the month of July, so we have this, if I go back, you can see that we have this wire, we have this one, which is the 4-core power cable. We have this, the harness wire, which is currently being used by most of the mines. So you can see from the estimation over here, the forecast. So for the month of July, these were the forecasts. We have 1,200 meters of the harness wire, which is going to be used. Then this is the actual, so we actually use this one. Then we have for the month of August, you can see that in the month when we recommended the 4-core power cable, you can see that they use this, if this is the forecast for the harness wire, then you can see that where we have that was where they use the 4-core power cable, which was used. Now we did some little estimation to see how we are saving costs for the company. So a forecast was done with the 1,200, which is here in the month of July. Now per meter of that wire, that harness wire is $0.56. So if you multiply this, this is what you are getting over here. Then in the month of August, which is this, if this is the forecast, this is the actual forecast, you can see it here. So they were supposed to pay what? $1,344. So you can see from the estimation over here that in the month of July, no cost was saved. But when we recommended the 4-core power cable, you can see that this is the amount that the company has saved. We have saved the company. Now, we also went further to do it for another mine where they do 28 shots in a month. So you can see this is the forecast if they are supposed to use harness wire. You can see over here, they use what for the 28 shots, they use 1120 of the harness wire. Then you can see this is the cost. This is the cost. Now, if we use the 4-core power cable that we recommended, you can see that this is the cost that was incurred over here. Okay. So now when we take this, even when you take the difference from this, you can see the cost that is saved. So you can see that in effect, we have saved about $5,132 for the company. Now, in terms of cedis, this is the amount that is given over here, which is about 58,000 Ghana cedis in terms of cedis. Now, you can see this a circuit, the test circuit continuity, which was procured by the company, the one we manufactured. You can see that 3 of them, the unit price is $718. Now they bought 3 of them, which is giving you this amount. So now they bought 3 of the short exploder to which we did at UMAT over here. 3 of them is also giving you this amount of dollars, which is here. So when you sum up this, they spent $10,674 on this blasting device. Now let's see something interesting over here. So this is the product from AIC, which was procured. Now, if you look at our own that we did, you can see over here that this was the total cost that we did this. So it's $489. Now, out of this, you can see that this is the total amount in cedis that was used. Now, compared to this is in dollars. The one here is in dollars, which is 10,674, compared to this one, which is 489 what? $0.81. Now you can see over here that this is converted into cedis. This is the cedi amount over here. This is what? The cedi amount, which is 5,608. Now, when you do this computation, you realize that the cost that we have saved, you subtract this 10,000 from the cost that's of our device. So we are saving the company about $10,184. When you translate this into Ghana cedis, this is the equivalent Ghana cedis. This is the amount that we are saving for the company. So now with that one, we are also able to go ahead and do some publication. So we have currently sent one paper, and the paper has come with major revision. We are currently revising it to be resubmitted for publication. So in conclusion, I will say that an optimum timing sequence should be introduced into pre-split blasting, which is currently going on. Then our research has also been able to identify failure mechanisms in the open pit. Then a locally made short exploder or continuity circuit tester for surface. So our device is working both surface and underground. So it has worked, and you can see it in the videos. And the engineers are also confirming it. So this research has also revealed cost-saving strategies with the short exploder, with the introduction of the 4-core power cable, which can also be used as a firing line instead of using the harness wire, and you can see the cost that was saved. Now, the following recommendations were made for future works. So the chamber should support us to make our product available for commercial use by mining companies. Now, in future works, we are planning of introducing, normally these blasting devices, it should be authorized people who should use it. So we are planning in our next production, we are planning to introduce a fingerprint. So if you are not a blastman, you are not authorized. So the fingerprint will allow you to be able to what? Use the device. So that's for the future one. Then we also have the dual purpose. Now we want to further minimize costs by combining both the circuit tester, which is used to check all the surface connection, then with the exploder. So we have 2-in-1, which will also bring that cost down. So that is what we are planning to do. Now the team is also currently, Madam Florence is also guiding us. We are also currently on to try and do some patent and copyright of our products. Yeah, so that's basically what we are doing. These are some references. Then in the acknowledgement, I would like to thank the Ghana Chamber of Mines. In fact, I'm very grateful for them giving me this award. In fact, this has really tested. This is, I must say that this is one of the works that I've really done in terms of research that has really opened so many things, so many doors and avenues for me. I'm very grateful to the Chamber of Mines for this grant. Then in addition, I would also like to thank the entire UMA staff and all the lecturers of School of Petroleum for their support. Then finally, thanks goes to the various mines for their support for carrying out this project. Yeah, thank you very much. Thank you very much, Dr. Ziga. Hello? Hello?
Hello, we can hear you, please.
Yeah.
Thompson, thank you. Sorry, I was having to phone.
Okay, thank you, Dr. Ziga.
This is question.
Hello, can we ask questions now or?
Yes, please, you can go ahead.
Yeah, please, I have a simple question for the second speaker. He mentioned that the flag 3D simulation was quite reasonable. I'm just wondering if there's a way that reasonable can be quantified. You have the real stuff and you have the simulation. What is reasonable? Is it like maybe 90% or how in engineering terms, how is certain quantified? I thought reasonable is very, very loose. Is there a way it can be quantified somehow? Thank you.
Okay, thank you very much. So concerning that statement, due to the factor of safety that was achieved, you could see that from the actual pit instability, it was seen that the failure that occurred at that particular surface, okay, so the failure that occurred at this particular surface was a circular failure. So from the factor of safety that was computed for from the simulation, being compared to the criteria, the failure criteria that is shown here, it was also ascertained that the failure that was occurring in the simulation was also a circular failure. Hello, sir.
Hello, Prof.
Yeah, please. Is the question answered?
Thank you for the Prof.
Unfortunately, I have some technical distance, so I didn't hear.
Oh, okay. Then
but it's internet problems. So.
Okay, I can take it again. So as I said earlier on, as seen in the failure that is occurring on the actual pit slope, we can see that the failure is a circular failure, the failure that occurred in the pit. And from the simulation flag 3D did, where we basically use the factor of safety that was calculated for to actually compare using the failure criteria that we have here. And according to the failure criteria, when the factor of safety is equal to or greater than 1.3, it means the failure that is occurring on the slope is a circular failure. And so from comparison to the failure criteria, it is noted that the flag 3D was able to predict that the failure that occurred on the actual pit surface was a circular failure. Hello, sir, please. Has it
Hello,
been
Prof.
answered?
Can you hear him?
No.
No problem. Please, Dr. Zika is having issues with the internet connectivity, so I'm going to stand in for him. There's a question in the chat box from Dominic Kagan. That's nice presentation. Please, I would want to know how the delays are assigned. Are they using surface delays or they have microchips that accepts the delays in the hole? That's question. And then 2, is the exploder at this stage only used for press plate blast? That's number 2. Thank you.
Okay, thank you very much. So with the first question,
thank you.
Okay. The electronic blasting equipment will be used. That will be used to program the delays, and this current research that is still going on. We are running the simulations. Then the exploder works for both surface and underground. It's a non-electric initiation system. That's what we are using for the second question. I don't know whether I've answered the question that the gentleman asked.
All right, Thank you very much. Dominic, I hope your question has been answered. Please, are there any more questions from the audience?
Hello?
Yes.
Yeah, please. My house to do with a blast exploder. I would like to know how many times can you use it before you can discard it, or is it like you buy it and that is it?
Okay, thank you very much for that particular question. Currently, as you can see, the engineers testing our device, you can see they were even recommending the device that it's really working very well. And for the past 1 month, this device has been used. So we've still not had any problem with it. And normally, if you look at this, you realize that always they have to procure this from outside in order to, they have to procure it from outside for you to be able to use. So our device currently, it has been used for the past 1 month and it's robust and there has not been any problem with it. So that's the robustness. And in terms of cost saving, the 4-core power cable can also be used at the firing line instead of the harness, where, as I've already shown in the diagram, the cost saving effects that is also associated with this. Yeah. So basically, that is it. I don't know whether I've answered your question.
Yeah, somehow answered, but I wanted to know if there's maybe some number of shots that you can do with it. Then after you achieve that shot, you discard it, or it's something that you can continue using.
Okay, actually, if you look at our device, the one that I showed you the image initially, if you look at our device, it's rechargeable. It's rechargeable. So you can recharge it. Unlike the one they were using, which I showed the picture, which is not rechargeable. Yeah. So our device, we made it in such a way that it's rechargeable. So you can charge it. Yeah. So basically, so at least it has been used for both underground and surface blast for the past 1 month. The device is working. Yeah.
Okay.
Thank you very
Doc,
much.
I also want to ask. Yeah, looking at
Go ahead.
looking at the terrain of our mining industry, the rough terrain and the dirt, the dust, the rain.
To talk about what is mine. To talk about petroleum, then I'm talking about mine.
Hello, can you come again, please?
Yeah, please. I was saying, Doc, I was actually looking at the terrain of our mining industry, how rough the dust aspect, the rain. Sometimes you have to blast even in the rain, and other climatic conditions. Is it suitable for the working, like our climatic conditions as it is in the mine?
Okay, thank you very much for the question. Yes, the device is suitable for our climatic conditions. It can be used for our climate conditions that we have over here. Yes, so it's working perfectly well. Yeah, so it can be used for our climatic conditions. Yeah, no other climatic conditions will affect it. So it's working. Yeah.
Okay, thank you very much.
Yes, sir. So the device is working. So you can listen.
All right, thank you. There's another hand up from Dominic Hagan. So please, you have the floor. You may ask your question.
Okay.
Yes, thank you. I want to know. So here we are talking about just the exploder. We don't have any accessory that comes with it, or we have our own detonators that comes with the product. Or do we resort to other manufacturers for that? And then probably we just have the exploder so that we can have a full view of what we are talking about. And then the harness wire. How certain are we that we are not going to have a cut from a fly rock? Have we done any tests that ascertain that we are not going to have any cut of a source? Or it is durable enough?
Okay, thank you very much for the question. Thank you very much for the question. From what I already said initially, the harness wire is currently being used, and you can see the cost estimation that I gave over here. So per meter of the harness wire is 0.5, depending on the length of the harness wire you have used. But if you have the one you have recommended, which is the power cable, the 4-core power cable, you realize that it becomes a firing line. So you can see in the diagram over here, mostly the harness wire after blasting, some you cannot use it anymore. Yes, most of the time you use it for 1 or 2 or 3 days, then it's off. But with this one, you can see the roller there. After the firing, you can still roll it and use it for another blast. Yeah. So that's the advantage of using the power cable. Yeah.
Okay, thank you very much. So if there are no further questions, Dr. Branson, we are grateful for your presentation. We are grateful for the answers to the questions. We are grateful for your time. And all those who ask the questions, we are also very, very grateful. So you may unshare your screen while we wait for the next presenter. Thank you.
Okay, thank you very much, Dr. Jamel. Thank you very much for the opportunity.
All right, so the next presenter will be Dr. Shadrach Fosu, the head of Department for Environmental and Safety Engineering. He will do a presentation on the topic Investigation of Water Saving Strategies in Gold Milling Circuits and its implication in processing engineering. Dr. Fosu, please, if you are ready, kindly share your slide.
Dr. Jamel, I think Dr. Fosu is not around.
Okay, let me try and contact him.
Jamel, if it's not around, I can come in.
Okay, Dr. Adamako, if you are here, then that'll be fine. You can take your presentation. So, audience, please, we will skip.
Hello.
Hello.
Hello. Indeed, Dr. Shadrach is not available to present. He has traveled.
Okay, Prof. Thank you very much for the
Yes,
information.
he's outside of the country. Yes, so the third presenter can go on.
Okay, Prof. Thank you very much.
You're welcome.
All right. So, Dr. Adamako, you may present. Okay, so
thank you
Dr.
very
Adamako
much.
is there. Hello, Doc. Let me introduce you properly because you're my head. Dr. Adamako is the head of Department for Geological Engineering this month he will share with us on his research on the topic or genesis of the Nkran Akwasiso gold deposits, Asanko mine, Ghana, orogenic versus intrusion-related mineralization, and the implications for target exploration in the Kumasi Basin. Doc, your audience are ready to listen to you. Thank you very much.
Okay, thank you very much, Dr. Moderator Jamel, for the opportunity to make this presentation. And I want to thank the Ghana Chamber of Mines for the funds to run this work. As my previous presenters have made, these kinds of works wouldn't have been possible without the very support from the chamber. And then I'm very, very grateful. I also thank my colleagues who are all have been supporting with the work we do in the department. Last but not the least, I thank the university for such an honor done us to make this achievement go on. So without much ado, I would like to now present on an ongoing study that we are carrying on the Asanko deposit, which is currently considered to be an orogenic related type mineralization. So based on some evidences we found, I would like to consider this approach to this work today. So the topic is on the orogenesis of the Nkran Akwasiso deposit Asanko, what it means for the intrusion versus orogenic related mineralization, and how that understanding can be used for exploration targeting in the Kumasi Basin. Sorry. My presentation will follow this outline from introduction through to recommendation. Yes, we know that increasing the mine life of every mine is the goal that all mines across the globe will always want to do. And such approaches include conducting successful exploration that can allow for the extension of the ore body or the discovery of new bodies that can add up to the tonnage in the mine. And in considering the exploration aspect, you know, because the increasing of the mine life could also be considered from other aspects as well. But today, looking at the target for exploration, we want to believe that in considering this approach, one must understand the deposit type that the company is working on. Not to say that this is not something that is not considered in some deposit. Yes, some deposits are considering the deposit type, but generally, the approach I'm come to present is not really a dominant consideration, which is the orogenesis approach. The orogenesis approach. So to understand the deposit type, one will have to consider the orogenesis approach as key factor in helping us clarify mineralization in the system. Now, in Ghana, due to the temporal and spatial association of what we would call the granitoids that have, you know, intruded the Birimian system, we see that most of these granitoids are associated with regional fractures or shear zones, and therefore exploration for primary gold is actually focused within these fractures or shear zones. These are what we call the orogenic related model, where orogeny means that mountain building processes in ancient time have created fractures within the earth crust, and then fluids that contain, you know, precious metals are able to access these fluids and then interact with various rock types and then deposit them. However, when we look across West Africa, we see that now we know that the Birimian extend across Ghana through West Africa, what we call the Birimian terrain. It extends across Ghana through West Africa. And in many parts of these West African and neighboring countries, like in Mali and the Ivory Coast and in Burkina Faso, there has been some evidence of granites or granitoids contributing directly to the Birimian gold budget. In other words, when we talk about this Birimian system, as I've mentioned, and then the orogenic events that have affected the Birimian system, we most often than not consider the orogenic system or the orogenic system to form our gold mineralization. There's no talk about intrusion related. So, however, in the West African zone, we see that granites or granitoids have also contributed. Now, when we say this, what we try to mean is that it is not as a result of shearing processes, but rather the granite themselves, which have, introduced mineralization in the area. Now, understanding the orogenic type related and then the intrusion type related has many implications for exploration. However, one of the biggest challenges, and I will talk about that later, one of the biggest challenges we face is that many times you can have granite systems or you can have magma systems synchronously, emplaced within the shear zones that have been created by these orogenic systems. So it makes it difficult to actually decipher between whether the mineralization is caused by a granitic system or the mineralization is caused by an orogenic system. And because both of them are occurring most of the time, it makes it a bit challenging. And that is why it becomes important or imperative that individuals or companies that are working in these kinds of system must make sure that they understand whether they are dealing with an orogenic system or an intrusion related system. And I will try to make an illustration of what I mean by this. Now, when we take the orogenic system, as we can see in this figure, we see this dark line here representing the shear zone contacts. This is where we are looking at as the shear zone, or what we call the shear zone corridor. This corridor has been assessed by granites or by granitoids, and this is typical of many of our, granite-hosted bodies or granitoid-hosted bodies across the globe, including Ghana. So we are quite familiar with the fact that the shear zone corridor has been opened up, and then during the orogenic period, some of these granites access these shear zones, and then they were involved in the mineralization process. However, when we want to look at the intrusion-related style, what we are trying to imply here is that the intrusion-related mineralization does not necessarily need a shear zone to be able to form. As we can see, outside of the shear zone here, we have granites that have intruded various portions of the terrain, and then that means that these granites are also possible sources of mineralization. Therefore, if you are mining in an environment where you think it's orogenic related, that the possibility is that you will focus only within that zone and will not consider the zones outside of this or fracture stretch or shear zone stretch. One of the other challenges is that because there's no fracturing or there's no shear zone on either side of this section, what will happen is that most of the granitoids that are outside of the shear zone are deeply buried because they do not have any access to even come further to the surface to be easily targeted for. All right, when you have fractures within the shear zone, then most of the granites can travel even to the shallow crust, and then they can form mineralization. However, if you are looking at intrusion-related systems, they could be in the shear zone, and then or else they could also be outside of the shear zone. When they are outside the shear zone, they are relatively much deeper compared to being in the shear zone. This is a geological map of Ghana showing us the Kumasi Basin, where my study is, the study is focused. This, I would say, this structural corridor here being identified as shear is where the Asanko deposits are located. This is what we call the Esankragua Fault. All right, and as you can see, it has been denoted by a subduction zone feature. All right, so these dark line here with these teeth, you know, suggest a subduction zone feature within the Kumasi Basin. And for the most part of mineralization exploration in Ghana, we have focused on the contacts between the Ashanti belt of metavolcanic rocks with the Kumasi Basin. And also on the other side, we can see the Seshri-Bibiani belt, which is also constituted by metavolcanic rocks and some volcanic sedimentary rocks. And along the contacts of these volcanic rocks and the basins, that is where we have the major mining or the major deposits located, like your Chirano and then Bibiani gold deposits, as well as up north, we have the Ahapo deposits. When you come to the Ashanti belt, you are having mostly Obuasi gold deposit, Pristia, Bogoso, and to mention but a few. So these structures had been the focus of our works from time immemorial, I mean, considering the mineralization style in Ghana. However, the basin locality now became a point of, you know, exploration, because these deposits, as we see here, had been also discovered within the Kumasi Basin. So when we talk about basins, we are normally talking about meta-sedimentary rocks that have been intruded by the Ebonian granitoids. And then when we talk about the belts, then we are talking about meta-volcanic rocks that have also been intruded by what we call the belt granitoids. So based on this observation or this scenario, Asanko is considered to be part of what we call the orogenic system by many researchers. However, during a visit and then discussions with company geologists, and then consideration of some literature review, and then some observations that were made on the deposit, there began to be a new thinking as to whether the Asanko's deposit system is an intrusion-related deposit, or indeed it's an orogenic deposit, or the case may be that both of these types of deposit systems are occurring there, where one could be an overprint of the other. So that is what this work, based on the new observations, tried to do. Now, going straight into the Asanko deposit, and particularly using the Akwesisu deposit as a point of reference, because that is where the majority and the clarity of the relationships in the deposit was observed and seen. And within the Asanko deposit, as I said, within the Kumasi Basin, and therefore you have meta-sediments, you know, being the bulk of the geological feature there, I mean, geological rocks there. And then these meta-sediments have been intruded by these granitoids. And in order for you to appreciate the relationships, I make a sketch of that observation so that it can be clear for us to see. Now, within the deposit that is hosting the mineralization and from which the company is mining from, we realized three major vein types. Actually, there are many different vein types in the deposit, but I consider that there are actually three main types that could really be considered for understanding the mineralization. The others are kind of minor or smaller features, and some of them are actually even splays of the ones, the major ones. So within the deposit, there are three major vein types that could be identified, were the VM, which I call the veins in the meta sediments, then the VG, which I call the veins within the granitoids, then the VC, which actually is the vein that cuts through both the VM and then the VG. Both VM and VG do not cross each other. So if you don't have any cutting relationship, it's difficult to tell which of these veins came first. However, VC cuts through them, so we can at least say that the VC vein is later than the rest. Then also there's another important information that we gathered from the company geologist, which is that the contact between the the granitoids and the meta sediments, that is where the highest grade of gold are mined. That is where the highest grade of gold are mined. So this became another important information because we are not seeing these veins cutting through the granites, and therefore it was difficult to say that it is the traveling of these veins across these both types of rocks that has actually caused an interaction at the contact. There is no cross-cutting relationship between VM and then VJ. So that became another point of interest as we look at this. So here came about the gaps and questions. Number one, although people are looking at this deposit as mainly an orogenic system, are there any features in the deposit that is suggestive of an intrusion-related model? Number two, what are the structural and physicochemical conditions that one can, tap into or identify that can really clarify the orogenic versus intrusion-related character? Then number three, are there any chronological clues? What is the timing between these veins and alteration within the deposit? And then under the chronological clues, we also look at the sulfide gold textures as well, because all of these can give information as to what we want to talk about. And for the interaction between the vein and the meta sediment, there is what we call in geology hornfels or baked sections, where because the vein, the granitoid is very, very hot at the time it intrudes the sediments, its contact also bakes the contact within the sediments. In other words, the sediment become very, very, very heated up and even changes, texture. Sometimes, most of the time, they become very, very fine grain, different from when you move away from that contact point. So these observations, these discussions led to the following gaps. And then based on the gaps, we have these three objectives. Actually, it's four if you want to consider the timing. In the proposal, we're talking about the chronological clues. The age data for the deposit has not been done, and it was part of this work, and unfortunately the data is not yet in, and so we look at the other three objectives to which of course satisfies the evidences that we are presenting here. So number one, to clarify the geological and geochemical relationships. Number two, to clarify the stages of mineralization, and then explain why the contact zone is of high grade. Why is the contact zone of high grade compared to the veins themselves? And then number three, establish the physicochemical characteristics of the ore-forming fluid. And mostly this is actually being done to understand where or what relationship the VM, VC, VG is having. So these are some of the hypotheses that I carried out, all based on the objectives. The main points are the contact relationship, the ore textures, the chemical property of the host rock, because the host rock here is a carbonaceous sediment, and that is what actually played a major role in the high-grade mineralization at the contact. And then oxygen isotope data. With all of these, I will try to now establish the geological and fluid relationships. And these are the methods that were employed as we try to conclude on this project. Now, to the results and discussion, I've already shown you, this is Fig 5 that I've already shown you the first part earlier, which is the way the Asanko mineralization or deposit is. And as I've previously mentioned, this is an intrusive rock that has gone into that has intruded the meta sediments. And these white lines we see here is actually a bending of the vertically oriented layers. If you like, right now they are metamorphic layers or foliations in the meta sediments. Now, based on this observation, I believe that the meta sediments had been acted upon by some orogenic events that has caused it to, align themselves vertically, and then the intrusions of these, the intrusions coming into that meta sediment have actually created, these bending, if you like, within the deposit. Away from where the intrusions are, most of the meta sediments are aligned vertically on each other, vertically on each other. So that is where the feature here, and this is a very important feature. Then number two, I show you photomicrographs of the kind of alteration that is occurring within the deposit. And most of these alterations, with the exception of the one that I mentioned earlier, where you have the high grade zone, along the contact between the the granitoid rocks and then the granitic rocks and then the meta sediments. The high grade zone is as a result of the possible interaction between the granite and the carbonaceous materials that are within that rock. So that is the first major type of mineralization we can talk about. The other one is within the granitic system, where you are having the alteration of sericite, the alteration of biotite to sericite. And most of these all mineralogy observations were made or were seen at the zones where sericite was replacing biotite, also in the presence of carbonate, right? So these are the kind of mineralization that we observed within the granitoids. Then the other one, the third one, is going to be within the veins themselves, where they are also mineralized. Now, based on these observations, it was also realized that at the contact zones, the main mineralogical composition or the ore composition was arsenopyrite, pyrrhotite, and pyrite. However, when you go to the core of the granite, the mineralization was pyrite and arsenopyrite, and that will have an explanation for that. Now, the next was to look at the geochemical relationships using the mass balance approach, and this is for the Nkranakwesiso deposit, where we combine, we try to understand the distribution of elements within the altered zones of the granitic rock, and to understand whether these can also be used as indicators for an intrusion-related system. And within the Asanko mine, molybdenum, tungsten, and arsenic were considered to be quite dominant metals, highly dominant within the Asanko deposit. And for many granitoid hosting deposits, molybdenum, tungsten, anomalous concentrations of these and then with copper as well, signatures of intrusion related association. The next was to also consider the the relationship of the Asanko deposits, the granitoids within the Asanko deposits, and how they can be related to the tectonic settings that is within the area. Remember, I said earlier that it was considered to be that the setting there was considered to be mainly a subduction zone environment. So using the rock classification of De Bon and Lefort 1983, I show you figure A, which actually is a mineral compositional control plot, where when we plot our data on these, we are able to see the controls of these major minerals within the granitoid systems. So at times you can have the granitoid to be altered, like in this case, I showed an example of a biotite being altered to sericite. But then the control of the biotite mineral is still there. We saw, if I can just go back for a minute, we saw this yellow line, which suggests this is the form of the previous mineral that has been pseudomorphically replaced by sericite. So which means that this biotite mineral was present before the sericitic mineral occurred due to the mineralization. And so when we look at this plot, we can see this is where the Asanko data is plotting. And then we see that most of is a biotite rich granitoid. And that also has implication for what we're looking at as the belt type, and then the S-type mineralization. So the Asanko deposits, granitoids, were mainly biotite-rich granitoids. Then we also plotted these granitoids on the ASI diagram, alumina saturation index diagram, and again, the Asanko granitoids are plotting within what we call the I-type zone. First of all, we are looking at the per-aluminous zone, which means that it has a lot of, it has more alumina content compared to sodium and then potassium. And that is what the per-aluminous actually means. And then the second point here is that the Asanko granitoids are S-type granitoids. In other words, they did not interact much with the sediments when they intruded the Kumasi Basin. So this is two important information that helps us to characterize these granitoids. And then the last but not the least in the geochemical classification is what I show you here, which is the I and S, and then the A-type granitoids. Now, if you look at this carefully, this is the I-type, S-type plots. And you and I will understand that when you are doing plots of any data set, if you take any plot whatsoever and you put it on the diagram, you have some plots. And sometimes people have been making some mistakes in just taking any of these plots and then, making their definitive answer to the character of these granitoids. I decided to use the granitoid classification model of Wallen et al. Because it contains both the I, S, and then the A. The A is what we call the anorogenic granitoid. However, this anorogenic granitoid system normally occur in zones where there is no orogenic events. All right. But then we can also look at it in terms of the tectonic setting that they form, which is in rift zones as well. So plotting these data set on Wallen et al., we see these are various granitoid data that plotted on this diagram. We see the Asanko ones are the reddish in color. We see that the Asanko granitoid. In fact, most of the granitoids in Ghana are straddling between the I and S type granitoids and the A type granitoids. And this, for me, I believe, is the one of the key factor in looking at why the Ashanti belt and then the Sefwi belt look alike. Is there the possibility that these two belts were together and then rifting separated them to their current position? You know, this data offers some clues to that. And so we considered that, and then we saw that the style of the intrusion or the formation of the Asanko granitoids might not be as has been previously thought about to be related to subduction zone environment. But from here, both subduction and rifting related events. And the Asanko is most likely to be the latest in this regard. Unfortunately, we don't have the age data as yet, so this will only be a speculation. But just looking at the geological trend from the Cape Coast Basin to the Asanko area, it's most likely that the Asanko is late in the orogenic process in Ghana. The last but not the least in terms of the, and sorry, that being late in the orogenic process in Ghana means that it is overlapping with the latest stage mineralization in Ghana. Now, last but not the least, I consider the oxygen isotope data sets, and these are the various results that were obtained looking at this model, where you have the metasediments data set, plus 12.8 is for the altered metasediments at the contact, and then plus 37, plus 13.7 per mil is further away from the altered mineralized zone. And then for the granite system, we have a range of 13.1 to 13.4. And then for the VM veins in the metasediments, the veins recorded these values, 13 to 14.4. The VGs recorded 15 to 16.0. And then the last but not the least, the VC, which is cross-cutting beef, was 18.6. So we could see that there are changes, variations within the vein systems and also the granitic rocks as well. And based on the overlapping similarities, based on the overlapping nature of the first three, well, the metasediments, I want to consider it to be because of the strong heat that was coming from the granitoid as it encountered the sediments. And that is why this value has gone as low as 12.8 per mil. However, the others are within range of 13.1 to 14.4. And so this means that the granite themselves have a range that is similar to the VMs. The granite has a range that is similar to the VMs. And if you want to take the altered granitoid, the altered portion of the sediments that is in contact with the granitoid, the lowest value being 12.8 for the altered portion, then we want to also think that the granites having 13.3.4, and then the VMs also having 13.34 plus 14.4 could be related in this regard, which means that is it possible that these VMs received fluids from the granites to form this structure during the orogenic process? Right, that is one of the things to talk about. So based on all of these observations in terms of the orientations of the sediments, in terms of the mineralogical controls, in terms of the distribution of arsenopyrite, pyrite, and then pyrrhotite, and then arsenopyrite and pyrite in the core of the granites, and then also the stable isotope data, which is part of the physicochemical characteristics. We try to develop a model, which is, number one, you have the metasediments, because they are metasediments, so we want to believe that they sedimentary, they were sediments at first. And therefore, we know that sediments will have to be deposited, horizontally or laterally. And then when they are done so, this became metamorphosed during metamorphism. And then you have this, your foliated or layering within that. And then during the orogenic process, these granitic rocks, these metasediments were now inverted, or they were now, uplifted to form vertically oriented metasedimentary units. Then during the rifting that allowed the various granitoids to be intruding these basins, the Asanko granitoid was access these openings and then began to enter that region. And as I said, these granitoids are most likely to be partly mineralized because of the data that we have on the granitoids themselves. Now, these black sections I interpret as fracture zones during the granitoid intrusion. And I want to think that these zones either were created during the orogeny or during the intrusion of the granite. These are common features in deposits in Asia and some parts of West Africa, where the fractures have been created by the intrusions of these granitoids. Then the vertically VM is now being filled by exsolution of fluids, or should I say partly exsolution of fluids that is coming from the granite. And we see this orange or yellowish part. This is the portion where we want to establish that is the contact between the granites and the metasediments. And therefore, these contacts, because of the carbonaceous material in the metasediments, these contacts became the zone for high-grade mineralization. Why? Because the granites are likely to have been oxidized, and as they interacted with a much reduced metasediments carrying carbonaceous material, there was a sharp change in the redox condition that allowed for deposition of gold within this area. Mind you, all these vertical veins we are talking about do not cross-cut the veins. Do not cross-cut the granitoids, and that is why this approach is suggested. And then later on, metamorphic fluids or fluids that were likely related to the orogenic event in the later stage now begin to infiltrate the area and generate other forms of vein systems. Because of the age data that is yet to come in, it's quite a bit challenging to connect these fluids to the veins that are formed in the granitic rocks, the mineralized veins in the granitic rocks. Those veins and this fluid that are likely to have changed the biotite minerals to sericite and then cause gold deposition within the granitic rocks. But anyways, we can see a sharp difference in the oxygen isotope data that is allowing us to propose this kind of relationship. And then finally, the last cross-cutting vein is in there. So to conclude, first of all, I look at my first objective, and then based on that, it can be seen that the intrusive and tectonic contacts were observed within the granite and meta sediments, where intrusive means that there were portions where the granite, entered, contacted the sediments, and then the portions where there were breakages in the this is the tectonic contact is what is revealing in the way the veins, the vertical structure in the deposit, vertical structure in the meta sediment during the intrusion of the granitoid are observed. Then the next one is that the mineralization contact is highly mineralized. Sorry, the contact is highly mineralized, and that is likely to have been produced by the granite getting into that system. Then the anomalous MOWAS is some feature that is commonly associated with granite mineralization systems, as well in some case with also metamorphic mineralization system or orogenic system, except that for the granite system, MO is on anomalously high. So that is why we can think of some kind of contribution from the granite system. Then the rifting tectonic setting was like the dominant tectonic environment during the emplacement of the granites. Then number two, the conclusion here based on the second objective was that we could identify VM, VG, and then VC vein relationships. There are other sets actually, but these we consider to be the major ones that influence the mineralization in the deposit. Then arsenopyrite pyrrhotite relationship at the contact was dominant, and then at the contact between the granites and the sediment was dominant, whereas the arsenopyrite, dominantly arsenopyrite was much in the core. And that also explains the difference in mineral association. I don't think this has also been considered, or this has not actually been considered by many researchers on the deposit. Next is that redox, based on this observation, redox potential is the dominant process for the high-grade mineralization at the contact, whereas the other mineralization within the veins could be related to the mixed fluid type. If you look at this diagram, I'm trying to say here that you have metamorphic fluids that is likely dominant at this stage, that probably mixed with some of the in magmatic fluids that caused mineralization. The last but not the least in this conclusion set is that in establishing the physicochemical characteristics, you at oxygen isotope in particular, and then it was revealed that VM, the isotope data from VM, the meta sediments, and the granite overlap, and therefore there could be some possible relationship between the mineralization styles occurring within these units. And based on that, there's a possibility that if not all of it, some of the fluids that may have been emanating from the granite likely form the VM mineralization. And then later on, you are having other metamorphic fluids that are related to the orogenic style coming in. So based on this observation and then data set, we will now want to conclude that there is the possibility of some form of intrusion style mineralization within the Asanko deposit, within the Esenkragua belt, where, if you remember, this we said was the zone that the deposits are occurring in. That's the Nkrankwesiso deposit, and then that's where the mineralization is occurring. And so if we are seeing some indicators of intrusion-related style mineralization, then my suggestion is that there's the possibility that with outside of the zone, we are having deep-seated mineralization that is yet to be tapped into. Possibly some aeromagnetic data has been collected, possibly some geophysical information has been collected, but I will invite a revisitation into looking at the data set and considering the possibility of the deep-seated granitoid system. Why? Because there are no shear zones in these regions, and therefore these granitoids will not or are not able to access this zone and then come up within the same level that can be observed in the shear zone. So if this is partly an intrusion-related system that has been overprinted by an orogenic related system, then I suggest that mineral exploration should also target zones outside this area. Sorry. Thank you very much for your attention, and we are grateful once again to the Ghana Chamber of Mines and the University of and to UMAT for the opportunity to carry out this research. Thank you very much.
Thank you very much, Dr. Adomaku. That was a very detailed presentation. And from a geologist perspective, I think that was a wonderful work that you have done with your team. And please, if there are any questions for the presenter, kindly put your hand up and then I will identify you and call you. Thank you. we wait for questions from the audience. Yes, Professor Andy Patton.
Yeah, Kofi, I won't let you go free, so I better ask you something. Quite an interesting study. And what I know is that in the Canadian environment, in the Canadian Greenstone Belt, it's quite similar to what we have in Ghana here, and they were all probably formed at the same time. So geology is an event that is worldwide. Some events occur at several places at the same time. I'm just wondering if you've seen some deposits, again, like I know the Canadian system quite a bit, any similar deposit that have the characteristics that you are looking at, that you have these basins being intruded by the granitoids and the mineralization. Is there similar deposits somewhere that can probably help you to refine your conclusions? Thank you.
Yes, thank you very much, Professor Andy, for your question. And yes, I appreciate that question because it's one of the topics that has always been going on. Yes, in Canada, as you mentioned, there are intrusion-related deposits like the Hemlo gold deposits that is considered to be an intrusion-related. Actually, again, many of these intrusion-related deposits were once considered to be subduction zone-related, or better still, were once considered to be orogenic, deposits. All right. So the Hemlo, the Malartic deposits, as well in Canada, have all been redefined or reconsidered to be intrusion-related gold mineralization. And even in this presentation that I made, I talked about even West Africa, in Mali, and then also Burkina Faso, and then also just close by us, La Côte d'Ivoire. Many of these deposits were once considered to be orogenic related. Further studies or further approaches are now picking out, not so many anyway, just a few that are actually showing these other signatures for intrusive related mineralization. So, and then for Canada, most of the deposits actually were formed in the Archean time, compared to Ghana and then West Africa, which is Paleoproterozoic. But in any case, as you rightly said, the geological activities are almost and always similar. And therefore, yes, we have some of these mineralizations that are now being reclassified as intrusion rather than orogenic. If I may also add, one of the things is because the fluids, most of the people that have considered orogenic mineralization have always looked at the fluid system being a low salinity fluid system. And that is actually one of the major characteristics that have been used to explain the orogenic system, because they are formed from metamorphic fluids. But however, from many work that has come up has also shown that even the intrusion-related system can also, gives similar indicators. And normally when it happens like that, these are very deep systems, intrusion-related systems. Thank you. I hope I answered the question.
Yes, thank you.
Yes, sir.
Thank you very much, Dr. Ademako. Please, any other questions? Do we have any other question for Dr. Ademako? Okay, I see that there are no other questions for Dr. Ademako. Thank you very much for your presentation.
Thank you very much.
Okay, I think there's a question in the chat. Hi, I have a question from Soma. Please, you can ask your question.
Hello, Doc.
Okay.
Hi.
My question is, I think that I agree with you on the fact that we could have some deep-seated, granitoids that are worth exploring.
Yes, please.
Seeing that they are very deep, I'm also looking at what methodologies could favor, because some of the superficial methods might not be able to help with the investigation. Probably geophysicists can do something on that. I don't know if it can, but then I think also the issue of the thickness of these granitoids sometimes seem to also have some limitation to it even being discovered, because of the skills that we have in relation to the sizes or the area that we run these geophysical surveys. So do you have any methods that you would recommend that we could employ to find some of these targets?
Thank you very much, Thomas, for your question. I think the first and foremost will be to consider, as you rightly mentioned, geophysics, because geophysics will help us to know to what depths actually these targets could be. First of all, and then talking about geophysics, we are talking about maybe ground geophysics, because at least the aerial geophysics will pick up some signatures that will need to be followed up by ground, and then to determine the depth at which we can go, and hit these signatures beneath the earth crust. When they are discovered, I guess the next thing would be what is the depth from the surface, right? And that will lead to whatever approaches that will be, and for that matter, if it is economically right, feasible to carry it out, that would be another question to look at. So I think personally, I may suggest ground geophysics that is going to detect, signatures beneath as deep as we can go. Those that have been already discovered in the shear zone is because of, as I said, the fractures. So the fractures during the orogenic process, all of those granitoids may have been coming at the same time, but then because of the fracture zones, these ones were able to access further and then come much closer to the surface and compared to the others. So I guess, if we look at geophysics, for that matter, perhaps that would be the first way to identify if these deep-seated zones are present. And then, of course, from that, when we know the technique, then we can tell how deep we can go, right? So I think these two steps could be considered, that. I don't know if I answered your question, sir.
So that's
Okay, with the response.
Yes, please.
No, this one. Thank you very much. So, is there any other questions?
Dean Block 1, Dean of FMNT, he has recommended. So you have to go to Dean of SPS.
Madam Kuba, please mute your mic.
Any other questions? Those who shouldn't like to talk, if you could write it in the chat box, I'll read the question.
Okay. Yes.
Thank you very much. Yeah.
Yes.
If someone wants to ask a question, or Dr. Dumako has a remark that you want to make.
No, sorry.
Oh, okay. All right. Yeah, we are grateful for your presentation.
Thank you.
And for your time. Yeah. So I don't know if that Ziga internet is stable now. So that, yes. So Doc, over to you.
Yeah,
You have a stable internet.
thank you very much for stepping in for me. Today I had some internet. I'm grateful. On behalf of the chair, Ghana Chamber of Mines UMAT Committee, I would want to express our deepest appreciation to the audience and then our presenters. I believe today's presentation was very detailed. Some of us have learned how we even apply hierarchical clustering in geochemical analysis. So it has been a good one today. And God willing, on the 22nd, we are going to have the postgraduate students who were also awarded. And then one other faculty member in the person of Dr. Cedric Fosu. So on the 22nd of September, we are going to have another presentation, and the time is still 10 a.m. Thank you all and have a great weekend. Bye-bye.